So we will be now looking into filter realization. Essentially, the design that we have done so far through mathematical approaches in finding the filter coefficients will be now put into a flow diagram, a signal flow diagram, which is a formal way of getting into realizing the filters in hardware. So with regards to FIR filters, there are two common realization methodologies that are possible. One is a transversal structure, and the other one is a fast convolution structure. The transversal structure is pretty straightforward, and we have seen similar representations before. So essentially, in this filtering, what happens is the input variable X goes into the filter, which has a delay element Z minus 1 and multipliers and an adder. Okay, so essentially it's multiply and accumulate operation, and that's nothing but the convolution expression as well. So we have seen this straightforward notation before, and the thing here is that the number of multipliers obviously will denote the order of the filter, and in this case, like if you go from n equal to 0 to n minus 1, we have n of those multipliers, so the order of this filter is n. Also, when you have more of these delay elements, they all add to the latency of the system. Okay. So this is one realization. It's a straightforward realization called the transversal filter structure. The second way is to do with FFT chips, fast Fourier transform chips, integrated circuits. Now, how we could do that is that we would be passing the signal and the filter coefficients through an FFT processor, and what we get is a frequency transformed variables, and then we do the multiplication and do the inverse Fourier transform to get your output signal Yn. Okay, so it's another way of implementing the filter structure, and in fact there are integrated circuits which does FFT very efficiently and in a very faster way. This is because of the advancements that has been made in the domain of designing integrated circuits, which exploits the properties of the fast Fourier transform. The periodicity, the symmetrical aspects are exploited to make the computation faster. Now, things that needs to be taken care in a digital filter design are essentially what's called the word length. Word length is here it's talked about the word length effects is how many bits we use to represent the variables. Okay, you would have come across various bit processors like 8-bit, 10-bit, 12-bit, and so forth processors. That word length, if it's 8-bit or 10-bit or 12-bit, will have a huge implication on the filtering performance. And also, we have seen before, in many times, the filter coefficients happens to be floating point representation, and the word length plays an important role there. Okay. So that's another thing that has to be taken care in a digital filter design is what is the word length that we would be using. Longer the word length has definite advantages, but we are wasting resources if in applications we don't need to have such a higher word length. And this is where, you know, techniques like the Pan-Tompkins techniques are pretty neat and efficient because they fully rely on integer coefficients in terms of the filter values. So word length is another thing to keep in mind, and word length is nothing but the bit size of the processor that we are working on. Compared to analog filters, digital filters have a lot of advantages, and I will summarize that after we go through the filter realization things. But the two aspects where digital filters do not give as good performance as an analog filter would be in the area of word length and also in latency. Okay, so those two things are kind of design choices that one has to make, so we don't end up in suboptimal performance using um, digital filters. So following up with the FIR filter implementation, the obvious next step is to look into IAR filter realization. IAR filter realization, as we have come across, does have the feedback loop, and so we have to see how we are going to represent that feedback. And there are three structures that are possible: direct form, and what has been shown is the direct form one. Standard representation here. There's an input, and the input variables are multiplied by the coefficient A's, as shown here, and the feedback, which is essentially coming because of the output y and being fed back into the system, is multiplied by the coefficients A's here. Okay, so this form of representation, as for the given example, has four delay elements. It has 5 multipliers, 1, 2, 3, 4, 5 multipliers, and all it needs is one adder. Okay, so this is kind of the resource assessment of the digital filter. So this particular difference equation, which is given here, needs 5 multipliers, 4 delay elements, and 1 adder. Okay, now what's this direct form 2? That next representation is essentially a similar thing, but what we have done is that we have added another adder. So this initial adder is just split into 2 adders just for representation convenience. And we could easily see this part of the filter corresponds to the numerator, this part of the filter corresponds to the denominator. Okay, so that's a simple change of the earlier configuration. Now, what that allows us to do is that, given that the filter, as you could see, I mean, we could always write the numerator and the denominator, and we can also transpose them. In other words, if I show the next diagram, it will be clear. So rather than having the representation written as nz times 1 over dz, which is what we saw before, we could also flip it to make it 1 over dz times nz, which also implies I can flip these two blocks. Okay, this could come here, that entire block diagram, and this entire block could go on the other side. Okay, without changing the input and the output notation. Okay, just a simple swap of those sub blocks will allow us to have a representation which looks like this. So if you see this representation, the first sub block is 1 over dz, the second is nz. At the outset, when you look into this direct form of representation, it might be confusing because now you're starting to see the coefficients b's closer to x. Okay, yes, it looks like, because the x coefficients typically were denoted by a's, but when you see b's, you might be confused. There is no room for confusion here. It's just because we have done this swapping of those sub blocks, and that has allowed us to bring this compact representation here. Okay, so this is the difference. So when we flip, the b's are on the left side and the a coefficients on the right side, and the x and y remain the same. So the direct form 2 is simple rearrangement of the direct form 1. Now, when you look into the block diagram, it really gives an idea. Okay, rather than having some redundant delay elements. Okay, so if you see this block, when the signal is passing through this block, it's getting delayed, and the same signal when it's going through the other block, it's also getting delayed here. Okay, so it's some kind of a redundancy in the system diagram. So why don't we combine the delay elements? So that's exactly been done here. So rather than having separate delay elements like in the previous block, we have combined the delay elements. And when we combine the delay elements, we have done something interesting here, is that we have saved two delay elements by this operation. Okay, so essentially in the beginning we had 4 delay elements. Now with the direct form 2, just by flipping NZ and DZ, we have got into a compact representation of saving 2 delay elements. The number of multipliers is still the same, 5 multipliers, but one additional thing is also that we have added one adder. Okay, so now you are getting an idea that the hardware resources could be optimized by simple rearrangement of the configuration. You might think, what would be the big deal of saving delay elements? Obviously, we are reducing the latency in the system. And in practical application, the filter order that we are considering is normally of a larger order. When the order is big, then we will have more of those resources requirement. So optimizing this at a block by block level really provides an overall efficiency in the design. So direct form 2 looks like this. And again, you have to be careful about when you look into this filter diagram right away, you might think, oh, there is something wrong because the B's, coefficient B's are on the X side. That's nothing but because we have done the swapping of the sub blocks of that. Okay. Okay, now there has been a question around how do we really extend the digital filters to higher orders. Okay, so far we are seeing very simple order filters. Simple order means orders which we can easily visualize and understand. And definitely in a lot of applications, the order of the filters are quite high. I mean, for example, if somebody is doing speech processing, the order of the filter could be anywhere between 10 to 20. Okay, so that's a relatively higher order. And also in other biomedical applications, when we deal with physiological signals, the order could be higher. Okay, so the higher the filter order, how do we deal with it? And one such a structure is called the cascade form. What the cascade form allows us to do is that basically it has these various sub blocks, and they are all cascaded to each other, as the name indicates. So for example, this filter h of z could be written as a product of 2 smaller filters, okay, without losing any mathematical notation here. So the mathematical thing could be real, because this kind of a representation, the Z domain, allows us to partition or have these factors with us. So though each one could be represented as a filter diagram. So here, for example, H0Z would be your block 1. This would H1Z would be block 2, and you can keep cascading and basically mimic a higher order filter through this cascading operation. This has a lot of advantages. The very first advantage is that if at all I have to change any of the filter coefficient, then I just need to change one of the sub block. I don't have to totally reconfigure the entire filter design. So let's assume as a design engineer, we figured out, okay, the filter coefficients have an issue, like either A1 has an issue, for example. Then if I want to modify A1 for the first filter, I would just come into that multiplier and change it. Okay, I don't have to change the whole filter design here. So it really allows us in the aspect of debugging if there is anything wrong in the hardware implementation. And also it allows us to increase the speed. Okay, so in this cascading operation, we can probably incorporate parallelism. Like, okay, in the first case, I would be working on H0Z. Parallelly, I could also work on H1Z. And given that pretty much all processors we are dealing with these days have parallel mechanism. This modular approach helps us to fast track the process. Okay, so it kind of increases the efficiency and the speed by reducing the latency in the system, the cascade filter. And typically that's been adopted in all practical design when we want to do a higher order filter design, especially when the order tends to be greater than a certain number. For example, if it's more than 4 or 6, the filter order, then we break this into small chunks of filters. It's easy to break because it's all represented by this function. Then I could always have that written as a product of 2 smaller functions, and this way we can have multiple filters realized. So that's a kind of the third approach of going with IAR filters. And these 3 designs are very commonly used. Now, what is the next step after the filter flow diagram is given? As I indicated before, the next step of this one is really to convert this into a hardware description language. Hardware description language. There are quite a few of those hardware description languages. Hardware description language, or they call HTL. And then you can also program this onto a chip, okay, an integrated circuit. There are commonly 2 ways of taking this into the IC world. One is called the ASIC, ASIC, which stands for application specific integrated circuits. Okay, so this is application specific integrated circuit, IC. Okay, now what it does is that once you decide the coefficients in the integrated circuits or in the filter design, then in the ASIC, it's permanently programmed on the hardware, on the silicon. Okay, so the chip permanently carries those filter coefficients, and we cannot change it later. So let's say you designed a notch filter which removes a 60 hertz frequency. You know those filter coefficients, and you know you're removing 60 hertz no matter what. So those coefficients can be frozen and could be directly programmed on the chip. Okay, so no changes that need to be made in future. So that's where ASICs come into play. Whereas there is another design, if you feel these coefficients, the filter coefficients, has to be changed over time, and you need a very general platform, a generic approach, and that something could be given using what's called FPGA, and it stands for Field Programmable Gate Array. Okay, so it's Field Programmable Gate Array. As the name indicates, it's programmable as we are in the real-time application in the field work. Okay, and gate array is just the hardware language that we are, or the hardware circuitry that we would be using. So FPGA allows this flexibility, and given that it's made a little bit general purpose, the cost of making an FPGA, initial costs are high, but if you do a mass production of FPGAs, then the cost comes down, substantially. And ASIC and FPGA are very much application dependent. It depends on the context that we are dealing with. So the choice for the hardware engineer is totally dependent on the type of filter that's been designed. Is it a fixed filter, which means the coefficients are not going to change? Or is it a filter where the coefficients will change over time and we need to adapt to the circumstances? Okay. We also can take the things into a microcontroller and microprocessor or CPU level. And in the CPU, it just becomes a regular computer type implementation where your coefficients are represented through the bit size that is given for the CPU. And obviously we talk about even higher performance CPU, which is called GPUs, the graphical processing units. They bring in a massive parallelism. They can handle very large filters, very, very large filters. And these large filters are also seen as what's called the neural networks, for example, and especially things like convolutional neural network is a form of deep learning. And in that case, we really need to go to the next level of processing, and GPUs and tensor processing are the latest things in handling really, really big data applications and AI applications. Okay, so that's kind of a very general and high level explanation of why we have been seeing these things and what really makes it to the eventual integrated circuit, the chips that we are talking. Okay, all our modern consumer electronics and other electronic devices, at the end of the day, they carry these small microchips that's essentially either built through ASIC or FPGA process. Okay. And with this being said, there are certain advantages of digital filters, and as we have seen in the implementation so far, one of the things is that definitely digital filters are only composed of very basic elements of whenever we talk about the resource requirement of a digital filter, we talk in terms of the delay, multipliers and adders. Okay, now the advantages of digital filters are that it gives me the flexibility to change my filter coefficients according to the situation that I'm in. Then we could always take it to things like FPGA to implement it. Whereas in an analog circuitry, that flexibility is not common. In other words, I cannot frequently change between the parameters that I need. And it's always the design tends to be much more in a fixed way. Okay. The digital circuits are not very much prone to temperature, thermal conditions. In other words, the values of those numbers that are represented in the digital filter do not change because the temperature has changed or because humidity has changed and things like that. Whereas in an analog circuitry, they're very much prone to the external conditions, and the design could change over time. So that's another drawback of analog circuits and analog filters. Digital filters, one of the main drawback is that because we have to implement using delay, if the delay is substantial, then it adds, and that makes the whole process quite slow. Whereas we don't face this problem in analog circuits because it doesn't have a delay elements in analog circuits. The other thing we need to keep in mind with the digital filters is the effect of word length. Okay, so if you need a robustness in your system design for robust application, the digital filters obviously are good. Okay, and if you need speed, then analog filters. Okay, and in cases where you really need to bring the best of both worlds, then people have gone into mixed analog digital circuit design. Okay, so obviously, and in this course, our focus is on algorithms and methodologies, and we won't be looking into a lot of details about how things look in the hardware level. There are other courses and other modules that talk about it, especially courses around what's called VLSI, very large scale integration. These are things that deal with circuit design in totality, and they look into the in-depth aspects of some of the things that I'm covering. But what we have done is that we have made sure our algorithmic design or our mathematical approach is friendly to the hardware. Okay, so we haven't done something totally mathematical, and at the end of the day, it cannot be physically realized. Okay, as you very much appreciate, there are many techniques available out there, very intense mathematics, but we may not be able to see this kind of a visual hardware representation diagram, which means it's impossible to take it to the microchip level. Okay, but what we are looking into this course specifically is techniques that will be very friendly if somebody has to put it on a chip level implementation. Okay, so with that, it really brings the whole filter design into a consolidation here. We have looked into different methods of designing. You have already implemented few filters in your MATLAB. We have looked into how these things could be realized, a filter realization, and essentially, this kind of forms the building blocks of pre-processing in a biomedical signal context. Now, in the subsequent lectures, we will see how we can use this for an analysis framework. Like how would we really now start to see the filter coefficients which were previously used for filtering noises and artifacts could be seen quite differently as features or in information that's present in the signal, which could be used for pattern recognition and classification applications. Thank you.